Okay. So Wednesday is the first exam. And the topics are everything from the start of the class up through vectors. And so to get ready for the first quiz, to get ready for any of the quizzes, what you do is you read through the notes and then, you remember what the quiz was like, just short answer questions. But that's not what the exams are like. The exams are like the homework problems. Okay, so to get ready for the exams, the best thing you can do is look back through the homework questions. This would take a bit of time, but I think if you have this time, the best way to get ready for it would be to go back through all the daily problems just one by one. And I know you don't have time to do them all, but you can look at one and ask yourself, do I know the approach to doing this? And if it just pops right to your head, then think, okay, you're good on that, move on to the next one. And then when you get to questions where you're a little unclear on what to do, spend a little time on those, And I think that's sort of a manageable way to go back through all of the daily problems and just make sure that you're ready. Yep.
And with the exams, will we have problems on there that are similar to ones that we did in lab, or no?
No, that's separate. Yeah, that stuff will be on the lab exams.
Okay.
Yeah, so think of, obviously there's overlap in material between labs, but think of labs and class as kind of two separate things. Any other questions about the exam? Okay. And then, with the test coming up, I'd be happy if anybody has any homework questions you want me to go over, things that were sort of unclear. I'd be happy to go over as many of those as you'd like today. If nobody has any of those, we'll just keep going with 2D kinematics. But does anyone have any homework problems you'd like me to talk about? Okay. All right, so last time we did get into 2D kinematics last time, didn't we? Did we? Oh my gosh, I have to look. I get confused because I have two different classes. And, okay, hold on. That just popped into my head. I might... Right. Okay, so we're getting into 2D kinematics of particles. And so far what we've talked about is just vector calculations. And now we're going to, the same way we did in 1D, we're going to define what position means, velocity and acceleration mean. And so we have to start by defining the position as a vector, and we'll call that the vector P. The arrow over the top means that something's a vector. The velocity vector V, and the acceleration vector A. Time is going to mean exactly the same thing it did in one dimension. That doesn't change. Time is still just turning on and off a stopwatch and looking what the values say. So we'll start by talking about the position vector. When we talked about the position in one dimension, do you remember I said before we can write position as a number, we have to choose two things related to stickers that you put down somewhere in the real world. Do you remember what those things were in 1D? You had to define the zero position and the positive direction, which then also defines the negative direction. Now that we're in two dimensions, it's going to be a little different than that, but it's sort of going to be a two-dimensional analog of that. So we're going to choose the location of the coordinate system origin and the orientation of the coordinate system. So which way the x-axis is pointing, which way the y-axis is pointing. This is you can think of this as the two-dimensional analog of the position equals 0 location and the positive direction. Okay, now it just has to do with a coordinate system. And once you've chosen these, the position vector P is the vector from the coordinate system origin. It doesn't say from the coordinate system. So whenever I write CS, I'm talking about a coordinate system. Coordinate system origin to the object. So like, for example, if the coordinate system is here, and the object is here, the position vector is a vector with its tail at the origin and its head at the object. And possibly a easier way to think about this, a better way to think about this, is remember that the components of the position vector the components of that P vector are just the coordinates of the object in the coordinate system. Okay, and obviously you need to know where your coordinate system origin is located and how it's oriented in order to come up with those coordinates. So for example, let's say that you have a coordinate system like this. And there's 1, 2, 3, 4 along the x-axis and 1, 2, 3 along the y-axis. And if the object is here, so this is the object, then the position vector is this. The coordinates of the object are positive 4, excuse me, positive 4, negative 3. And so the position vector written in the vector component notation is 4, negative 3. The units for position, and this is something that's going to keep happening in 2D. The units that we used in 1 dimension are the same as the units we'll use in 2D. So for position in 1D, the units were length. And so in 2D, the units are length. And that means that the SI units are meters. So we're just always going to deal with position in meters. And then based on that position definition, now we're going to talk about what velocity means. So we'll define this velocity vector. In 1D, this was true also. Velocity is a measure of how quickly the position is changing. And one thing that means is a velocity vector of 0, like this, means the same thing as a constant position. Okay, so if the velocity is 0, the object's just staying in a single location without moving. So I brought this up and mentioned it a few times when I was introducing the idea of vectors. Vectors have two properties. Any vector has two properties, and these are magnitude and direction. Remembering these two properties is especially important with velocity because velocity is really breaks up nicely into these two things. So this is especially useful in thinking about velocity. So the velocity vector its magnitude is the object's speed. And its direction is the direction the object is moving at that instant. The units for velocity, just like always, are the same units that we used in one dimension. So anytime you're talking about velocity, you have to use units of length divided by units of time. And that means that the SI units have to be meters per second. I didn't say stuff like this about position. Really, with position, the main thing that you have to remember about position is just that think of it as the coordinates of the object. But there are three important things that you need to remember about velocity as you're doing these problems. So three important facts about the velocity vector v. The first one is often in problems, you're going to be given the velocity as a speed and a direction. The other things, not so much. Position vector and stuff, it won't be broken up into magnitude and direction that often. But often, you'll be given the velocity vector as a speed and a direction. And you'll have to then calculate the components based on that. So for example, a problem will say something like, at the start of the motion, an object is traveling 10 meters per second. So that's the speed at an angle of 30 degrees above the horizontal. In order to do math with really any vectors, you need to break it up into the components. So you would go from here and say your coordinate system is like this. This velocity vector at the start of the motion has a magnitude of 10 and makes an angle of 30 degrees with the horizontal. And so then the velocity vector components are 10 times the cosine of 30 degrees for the x component, 10 times the sine of 30 degrees for the y component. And that comes out to be about 8.66 5.0. So probably more than half of the problems you do, you're going to have to come up with the velocity components from a speed and a direction. Also, while I have it written like this, when we eventually get to equations, we're going to see these components broken up separately, like we're going to deal with them separately in equations. So another way to think of this is that the x component of the velocity is 8.66. And the y component of the velocity is 5.0. Okay, that's the first of three things you need to remember. The second of three things you need to remember is if an object is dropped, then at the instant it's released, I'll just say at release, its velocity is the same as what it's dropped from. So if an object is dropped from the top of a bridge, the bridge has zero velocity. So when you let go of the object, it has zero velocity. And then it'll start accelerating down. If a car is moving 30 miles per hour along the highway horizontally, and you let go of a set of keys or whatever, a bird, a fish, an elephant, whatever it is, when you let go of it, the velocity is going to be 30 miles per hour horizontally. And then gravity will make the velocity change over time from there. Okay. That can be a little tricky to wrap your head around if you imagine dropping a feather or a balloon or something out of like a car moving on a highway, because it looks basically like that thing just isn't moving at all. But just what happens is, say you have a balloon and you're going 60 miles an hour on the highway. You hold it out of the window and there's a lot of, air resistance on it. it's hard to hold it still. But the instant you let go, it is moving 60 miles an hour. It's just that it slows down so fast because of the air resistance that it feels like it never was moving that fast. Okay. So, for example, let's say if a ball is dropped from a vehicle that's moving 20 meters per second horizontally, well, if this is the coordinate system, this is the velocity vector of the vehicle. It's horizontal with a magnitude of 20. And so what are the components of that vector if that vector has a magnitude of 20? Remember, once you put the tail at the origin, you can think of, you can just think about the coordinates of the head of the vector. So what are the coordinates of the head of that vector? 20, 0, yep. So the velocity of that vehicle is 20, 0. And so the velocity of the object is 20, 0 at the instant it's released. Okay. And then the third thing, this one, these first two maybe are what you would guess would happen. The third one is probably not quite exactly what you would guess. So pay a special attention to this one. So in 2D, when a projectile reaches the highest point in its flight, if I made you guess about what happens at the highest point in the flight in 2D, probably most people's guesses would be that the velocity is equal to 0. And that's on the right too. What is true is the y component of the velocity is equal to 0. This is for our coordinate system, y-axis pointing up, which is what we're always going to do. But it doesn't say anything about the x component of the velocity. Okay, and so if you want to understand why that is, I think this is kind of a good intuitive idea of why. So imagine that this is a pro baseball player. And he throws this ball, okay? As hard as he can. And imagine that somehow you had figured out where that ball was going to reach its highest point. And so before he threw it, you go get a ladder, set it up, and stand at the top of this ladder. Like that, okay? And my question is, so if your head is right where that ball is going to be when it reaches its highest point, is this a good idea? If the velocity if the velocity vector was entirely 0 when the ball reached the highest point, that would mean that this thing is slowing down, slowing down, slowing down, reaches the back of your head just as it gets to 0 speed, and it just gently nuzzles up against your head, and you can hold it, tenderly. But that's not what happens. The Y component slows down, gets to 0 at that point. The problem is the X component of that velocity stays basically the same the whole time. And so if he throws this ball at 100 miles an hour, when it hits your head, it's still going 90 miles an hour, and that's, terrible for your head. So this is just supposed to be an explanation of why you should not do this. And why you don't know anything about the X component of the velocity at the highest point, only the Y component. All right, so those are the 3 things to remember as you work with velocity. Anybody have any questions about those? And then the last thing we have to talk about is the acceleration vector. Just the same way that velocity measures how quickly the position is changing, the acceleration is a measure of how quickly the velocity is changing. And so because of that, an acceleration vector of 0 means the same thing as a constant velocity vector. Okay, you can think of those as synonyms. It's just 2 different ways of saying the exact same thing. Remember that in 1D, so this is kind of a big deal for acceleration. In 1D, a non-zero acceleration means that the speed is changing. There's no other way around it. So non-zero acceleration means the speed is changing. In 2D, there's a whole new kind of thing that's introduced that didn't exist in 1D. So in 2D, a non-zero acceleration means one of 2 things. First, it can mean that the speed is changing. But now there's a whole other possibility. So and or, it can also mean that the object is turning. If you imagine being in a giant parking lot going around in a tight circle at, say, 20 miles an hour or something, you know that feeling of like your body wants to go to the outside, your seatbelt is holding you in, you kind of have that feel in your stomach. That feel that you have is the feeling of acceleration. You're accelerating. Even if you're watching the speedometer the whole time and keeping the speed exactly constant. That acceleration is coming from the fact that the velocity is changing, not because of the speed, but because the direction of the velocity is changing over time. Okay? And in lab this week, we're going to spend a lot of time thinking about how to visualize acceleration in two dimensions, I mean. Okay, units for acceleration. Just like in 1D, our length divided by time squared. And the SI units are meters per second squared. Okay, and there's really only one thing that you need to remember about acceleration. Almost all of the two-dimensional calculations that we're going to do are going to be projectile motion free fall problems. So remember, in free fall and projectile motion, the acceleration vector is always 9.81 meters per second squared down. And just like in 1D, it doesn't matter what direction the object is moving, if it's in free fall or projectile motion, if it's on the way up or going horizontally or going down or whatever, the acceleration is always down. Gravity is just always trying to pull things down. Okay. So if you choose your y-axis up, which is what we're going to always do. So if you choose your coordinate system y-axis up, then the acceleration vector is 0 for x, negative 9.81 for y in meters per second squared. And this is something that you'll see sometimes, so I just want to bring it up here. Positive 9.81 meters per second squared is called lowercase g. So if you ever see that lowercase g, remember that that's the positive value of 9.81 meters per second squared. The negative is just, remember, that's just a direction. So the actual acceleration doesn't have a sign associated with it. You have to put that sign in once you choose your coordinate system. Okay, so now we're going to do the same thing we did in 1D after we defined all these things. I'm going to define the constant acceleration equations, and then I'm going to give you some general steps for using those equations, and then we'll just do a bunch of example problems. So next are the constant acceleration equations. In 2D. And we're going to define our variables sort of similarly to how we did it in 1D. The initial position vector and the initial velocity vector are the position and velocity when time is equal to 0. And the position final and the velocity final are the position and velocity at time TF. So when you turn the stopwatch on and when you turn the stopwatch off. The only difference is now those are vectors. And in all these equations, an x subscript means the x component of a vector. and a y subscript means a y component. Okay, so I'm going to start by just writing out the three equations that we had before. But I'm going to leave a lot of extra space because we're going to fill stuff in. But I just want to sort of bring out how the ways that this is similar to what you've already seen. So the first equation is VF, and I'm going to leave a little space there, is equal to VI with a little extra space plus A extra space times TF. Okay, and then leave an extra line and go down to the second equation. So the second equation says PF is equal to PI plus VI times TF plus 1/2 A TF squared. And then again, leave an extra line. And the last one says 2A times the quantity PF minus PI is equal to VF squared minus VI squared. So those are the 1D equations that we've seen, right? The only difference in 2D is now we're going to have one of these for all the x components of the vectors and one for all the y components. So I'm going to just copy this, but copy each one of these equations down below the one that you just filled in, okay? Okay, and now let's think about what values are vectors and what values are not vectors. Any velocities, positions, accelerations, those are all vectors. So we're going to put vector components in those. Time, final, is not a vector. That's just a number. So we're going to leave that one alone. So in this first equation, what? So in this first equation, it's going to say VFX is equal to VIX plus AX times TF plus E. In the second equation below it, it's going to say VFY is equal to VIY plus AY times TF. And then we're going to go down and do the same thing in the second pair of equations. So PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. And then in the next one, put y's in for all of those. So PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. And then for the last two, 2AX times the quantity PFX minus PIX is equal to VFX squared minus VIX squared. And then for the last one, 2ay times the quantity pfy minus piy is equal to vfy squared minus viy squared. So if you think about it that way, it's really, you don't need any more brain storage space for this. It's really all the same stuff you've seen before, just broken up into x's and y's. And now I'm going to go through, okay, well, just to make it extra clear, you know, notice that for each one of these, we have an x equation and a y equation. The only thing is, anytime TF appears, it's the same TF that appears in both of those two. Okay, so here's a set of general steps for using these equations. They're going to look very similar to the steps for one dimension. So this is the general steps for 2D constant acceleration equations. So who remembers step 1 for one-dimensional constant acceleration problems? Yeah, that's right. So the first thing we do is choose a 0 position, a positive direction, and when the stopwatch goes on and off. Now we have the new version of that, but it's still the same idea. So step 1 is we're going to choose an origin location, and you can still think of that as putting a sticker somewhere down in the real world. I'll say coordinate system origin location. Then you also have to choose the orientation of the coordinate system. So which way the x-axis points, which way the y-axis points in the real world. And then a time equals 0 instant and a time final instant. What's the second step in 1D constant acceleration problems? List out the variables you know and the variable you're trying to find, okay? And remember, in one-dimensional problems, we only had 6 total variables, so we could just go through them one by one. Well, now we have more than that because we have x and y components for almost all of these. But I'm still going to write it sort of the same way. So, hold on. So we're going to list out the variables we know and want. And the list of variables is time final, acceleration, but now acceleration is a vector. Initial position is a vector. Final position is a vector. Initial velocity is a vector. And final velocity is a vector. And so this is just one variable because it's still just time final. But acceleration vector is 2. And all the rest are vectors, so all of the rest are 2. And so like if you add these all up, now you're talking about a list of a total of 11 total variables. Third is now trying to find an equation that works. What it means for an equation to work is we're trying to find an equation that has the wanted variable and every other variable is known. And now just like with 1D, sometimes it's the case that you can't find an equation that works. And so in those cases, I'll put those in parentheses. If no equation works, try to find an equation to solve for time final. And then go back to step 2. And in 2 dimensions, the reason that it's so valuable to find time final is if you look at these equations, time final is the only one that goes back and forth between x and y components of equations. So a lot of times what you'll get, and most often the one it'll be is this PF equation, but a lot of times the strategy you'll take is no equation will work to find the variable you want. So you'll use, like, say, the y equation to find TF. And then once you've found TF, you'll plug that into the x equation to solve for the variable you want. We'll see that happen a bunch of times. Okay, so far this is all just kind of theory stuff. Does anyone happen to have any questions about any of this? I think it'll start making a lot more sense once we start going through example problems. And I'm just going to try to very carefully go through the steps so you can kind of be systematic about it. Okay, so the first example, so let's say that a ball is thrown horizontally at a speed of 10 meters per second from a height of 4 meters. How far away horizontally will the ball hit the ground? Okay, so let me draw a picture of what's happening. So here's the ground. And we're starting out with this ball being thrown horizontally at 10 meters per second from a height 4 meters off the ground. And the ball is going to start out horizontal like that, and then it's going to curve down due to gravity, follow a parabolic path, and hit the ground here. And the question is, what's this distance? Any questions about what we're doing? Okay. So the first step is to choose a coordinate system, an origin, and an orientation. I'm always going to choose the y-axis up. One thing I'm almost always going to do is I'm almost always going to have the origin on the lowest spot that's kind of referred to in the problem. In this case, that would be the ground. And I'm going to have the y-axis pointing up. So my coordinate system is going to look like this. Okay. So that deals with the orientation and it deals with the location of the origin. And now we have to think using the same reasoning as with one-dimensional problems. What are we going to consider the instant we turn the stopwatch on, and what's the instant where we turn the stopwatch off? So when do we turn it on? When it's thrown, let's call it the instant it's released. These choices, remember, are always based on the instance when we know information and when we're trying to find information. So we know some stuff about the velocity and the position when it's released, so that's a good spot. And then time final, what's that going to be? Yeah, when it reaches the ground level. And now we can think about what variables we know and want. Do we know what the stopwatch says when the ball hits the ground, when it reaches the ground level? No. Do we know the acceleration? In free fall and projectile motion problems, we always know that. So the acceleration as a full vector is 0 for x, negative 9.81 for y. Do we know the position at time 0? Remember, position is just the coordinates of the object. So the question is, at time 0, when the ball is released, do we know what its coordinates are? 0 for x, 4 for y. You see that? So initial position is 0, 4. Do we know anything about the position when at time final? We're trying to find the x position, right? We're trying to find the horizontal position. But we actually know the y position because you can see that when it reaches the ground level, the y coordinate is going to be 0. And so PFY is equal to 0. So these variables, sometimes you'll know like one component and not know the other one. Do we know the velocity at time 0? Yep, and remember that it's a vector, so we have to come up with the components. So this would be like, I'll draw the coordinate system. We know that that velocity vector is this. So what are the coordinates of the head of that vector? It's right, it's 10 for x, 0 for y. And then do we know the velocity when it reaches ground level? No. So this is what we have. So what we'd like to know is if there's an equation out of those 6 constant acceleration equations that has PF in it and everything else in it is known. It's feels like kind of a daunting task to go through all 6 of those equations. But one thing that can help you a lot is they're like 3 of those equations are x equations and 3 are y equations. And there's no y components in x equations and vice versa. So if we're trying to find p of x, all we have to check is the three x component equations. So is there an x component equation that has p of x in it and everything else in it is known? And the answer is no, because we don't know v final. So no equation works. And so instead now we're going to try to find time final. Okay, so is there an equation that'll let us solve for time final? This one will work. Pfy is equal to Piy plus Viy Tf plus 1/2 Ay Tf squared. And we can check that it works the same way we always have. It has Tf in it. And then just go through, do we know all the other things? Pfy we know, Piy we know, Viy we know, Ay we know. So this one will work to find time final. So if I plug those in, we got 0 is equal to 4 plus 0 times anything is 0. So this term is 0. Plus 1/2 times negative 9.81 times Tf squared. So 0 is equal to 4 minus 4.905 Tf squared. And so 4.905 Tf squared is equal to 4. Divide both sides by 4.905. And you get Tf squared is equal to 0.815. And so Tf is equal to, remember, if you take the square root of a variable, the answer can be plus or minus. So we have plus or minus 0.90 seconds. And then do we want the positive or the negative time?
Positive.
Positive, yep. With time, it's easy. We always throw away negatives. Okay, problem's not done yet, but now we have time final. So now now we have this one more bit of information. And now we can go back to looking for an equation for Pfx. And the one that works is this one. Pfx is equal to Pix plus Vix Tf plus 1/2 Ax Tf squared. So Pfx is equal to 0 plus, what's Vix? Um, 10, right? So 10 times 0.90 plus, now this is one that's really easy to enter wrong. What's Ax? It's 0. Okay, like you're used to putting in negative 9.81 for A, but remember that Ax is 0. Only Ay is negative 9.81. So this stuff all goes away. And so we have that Pfx is equal to 9.0 meters. Okay, any questions about that? So I'm not going to give you an assignment for Wednesday so you can look stuff over for the test. And so then I guess next Monday we'll just keep going with this stuff in class. And by about halfway through the class on Monday, I'm going to start just writing problems up there, giving you time to work through it, and we'll do it that way. And little by little, this will feel natural, I think. Okay, that's all.